Hello everyone, this is Ketish here. In this video, I'm going to go through the AQA Combined Science Physics Paper 2 from 2024. This paper 2 is 1 hour 15 minutes long and it's tested on three main topics: forces, waves, and magnetism and electromagnetism. And it has 7 questions in this paper. So let's have a look at question number 1. Question number 1 is on the topic of forces. Figure 1 shows a skydiver jumping from an aeroplane. The skydiver is accelerating downwards. Which forces causes the skydiver to accelerate? It's not electromagnetic, neither it's gravitational force, yes. It's not magnetic as well. Which forces increases as the skydiver accelerates? And that would be air resistance. And it's not normal contact force. For that, the person should be in contact with the surface, and it's not tension because they're not hanging by a rope or anything like that. Figure 2 shows the two forces acting on the skydiver a few seconds after jumping from the airplane. So you can see there's a downward force of 600 newtons, which is the weight. And 150, which is the air resistance. Sometimes called the drag force. So 1.3, calculate the resultant force acting on the skydiver in figure 2. So the resulting force is the overall force acting on the skydiver. So you've got 600 downwards and 150 upwards. So you take away one from the other. So 600 minus 150 should give you 450 newtons. 450 newton. Question 1.4. Eventually, the skydiver stops accelerating and falls at a constant velocity. What is the resultant force acting on the skydiver when falling at a constant velocity? Now, for the person to be falling at constant velocity, the forces should be balanced, or the resultant force should be 0. So what is the resultant force acting on the skydiver? Right? It should be 0. If there was any force, then the person would be accelerating. What name is given to the constant velocity of the skydiver? And this is terminal velocity. Terminal velocity is the maximum velocity reached by an object when it's falling through the air. Figure 3 shows a velocity time graph for the skydiver. As you can see, the time in seconds is on the x-axis, and y-axis is the velocity in meters per second. So the line increases steadily in the first 5 seconds and starts to slow down in the next 10 seconds, and after about 15 seconds it's more or less is actually the same. So if I was to extend that line from that point onwards, it's actually terminal velocity, straight line. So how many seconds did the skydiver accelerate for? So you would find from the graph where it's the line is actually starting to go up, right? And right up to 20 seconds, after 20 seconds, the line becomes flat. So the skydiver is accelerating up to 20 seconds, or for 20 seconds. What was the constant velocity of the skydiver? So that is where is it the flat line. So if I was to draw a straight line, let's see if I can manage to do this. Nope. Right, let me try that again. There you go. You would need to use a ruler, so it's just one box above this halfway point, so that is 46. So each box is 1, so that's 46. After opening a parachute, the skydiver fell at a constant speed of 3.6 meters per second for 25 seconds. Calculate the distance traveled by the skydiver during this time. So they have given you the equation. Distance traveled is the speed multiplied by the time. The speed is 3.6 multiplied by 25. That gives you 90 meters. 90. That brings us to the end of question number 1, and let's have a look at question number 2. Question number 2 is again on the topic of forces. Figure 4 shows a person using a Newton meter to measure the weight of a suitcase. So you have a handheld Newton meter and a suitcase is hanging onto the Newton meter. There is a pair of forces acting between the suitcase and the Newton meter. How does the force on the suitcase compare with the force on the Newton meter? Now, the force on the suitcase compare with the force on the Newton meter, because it's hanging, it's not moving up or down. The forces should be balanced, right? For it to be balanced, the forces should be of the same size. Which statement describes the directions in which the pair of forces act? Now, the weight is acting down, and the upward force, let's have a look at the diagram again. So, the weight of the suitcase is acting downwards, and the Newton meter is pulling the suitcase upwards, which is basically the tension. Right? So, these two forces should be balanced because it's not moving. And how are the forces acting? They are acting in opposite directions. What is the weight of the suitcase shown in the Newton meter? So let's have a look at the diagram again. So you have 180, and that's 10 divisions. I'm pretty sure that's 10. So let's count it from 0. So 1, 2, 3, 4, 5. Right? That's 10. So which means that's 2 lines just below 200. So each of those lines is actually small lines is 2. So if I take away 4 from 200, 200 minus 4 gives me 196. Right? Each of those small divisions is 2. So that's 196 newtons. Calculate the mass of the suitcase. Gravitational field strength equals 9.8. Use your answer from question 2.3 and the equation. So we have to use this 196 in our answer. So our weight was 196. 196 divided by 9.8, which is the gravitational field strength. That gives us 20 kilogram. The suitcase is loaded onto an airplane. The airplane takes off and its height above the ground increases. The airplane then flies at a constant height. Figure 5 shows how the gravitational field strength in the airplane varies for the first 25 minutes of the flight. So as you can see, gravitational field strength, they haven't given you numbers here. So it's starting high and then it goes down and then it actually remains constant. Describe how the weight of the suitcase will change during the first 25 minutes of the flight. Use figure 5. Now, because they haven't given any numbers on the y-axis, we can't actually refer to any numbers, but we still can if we want, because this should be 9.8, right? Which means that's 10. So this is 2, 4, 6, 8, right? So that's 2, 4, 6, 8, and 10, and that should be about 9.8, because at the start, time in minutes, at the start it's on the ground and it's actually going down, right, to about 8.4, right, or 8.5, 8.4. This is actually 8.4, let's say, right? Right, but we can't use the numbers here, so we are just simply going to describe how does the weight of the suitcase will change in the first 25 minutes. Well, between 0 and first 15 minutes, the weight goes down, and then it stays the same from 15 to 25 minutes. So here's the answer. The weight decreases from 0 to 15 minutes as the gravitational field strength decreases. That's 1 mark. Now, the reason this is happening is because the airplane is actually going or increasing in height. When you move further away from the land, right, as the height increases, the gravitational field strength decreases. 2nd mark, the weight then becomes constant at 15 minutes. Why does that happen? Right, so to say that the weight becomes constant is 1 mark. At 15 minutes to stay, or after 15 minutes, is your 3rd mark. The reason that this happens is because an airplane, if that line is actually the ground, right, the airplane takes off and then literally flies at a constant height. So the gravitational field strength decreases as the height increases here, and then the height is remaining the same, so the gravitational field strength remains the same. That brings us to the end of question number 2. Let's have a look at question number 3. Question number 3 is on the topic of waves. Figure 6 shows an electronic whistle used by a referee in a football match. So the electronic whistle, and you have a button here which makes the whistling sound. When the button is pressed, the whistle emits sound waves that travel through the air. What is transferred by sound waves as they travel through the air? Well, the sound is a basic type of energy, sound energy. What is a typical value for the speed of sound in air? Now, the speed of sound in air is 330 meters per second. It ranges between 330 to 340. So average is about 330. The whistle can emit 2 different sound waves, A and B. Figure 7 shows 2 different sound waves as displayed on a screen. The sound waves are drawn to the same scale. So wave A, the waves, as you can see, are much closer together. Wave B, the waves are actually a bit spread out. Right? Complete the sentences to describe a difference and a similarity between the 2 waves. So the difference is, in wave A, the waves are closer together. This is high frequency. When the waves are together, it's high frequency. And that's low frequency. Frequency is the number of waves in 1 second. Right? So if I take, how many boxes do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 boxes. If I take these 10 boxes as from 0 to 1 second, I have 1 wave, 2, 3, 4, 5 waves here. So the frequency is the number of waves in 1 second. So that's 5 hertz. And here I have 2 waves. So the frequency is 2 hertz. So it has low frequency here. What is the similarity between them? Well, they both are the same height. Now the height of the wave from the middle point to the peak, right? So that's the peak, and this is the trough, which is the bottom of the wave, right? That is called the amplitude. So they both have the same amplitude here. So wave A has a greater frequency. Wave A has the same amplitude as wave B. A wave has a frequency of 4 kilohertz. So this small k means kilohertz. Now kilohertz, which of the following is the same as 4 kilohertz? Now a kilo is 1,000, right? 1,000 is equal to kilo. So 4 kilo is 4,000 hertz. Calculate the period of wave A. Use your answer from question 3.4, which was 4,000. Yeah. So 1 over 4,000. So the wave period is 1 over 4,000, and that gives me 0.00025 seconds. Sound waves in air are longitudinal waves. Complete the sentence as described in sound waves. Sound waves. So what are longitudinal waves? Now there are two types of waves, longitudinal waves and transverse waves. Longitudinal waves is when the particles move back and forth like this, right? The particle, if that's the particle, it's oscillating parallel to the wave direction. In a transverse wave, the particle is actually moving up and down, not sideways, right? Well, the wave is actually going in this direction. And transverse waves are usually drawn like that. So when sound waves travel through air, they create areas of, right? Now for this, it's best to actually see what a longitudinal wave or sound wave actually looks like. So if you were to look at an image of sound wave, so here's an image of sound wave. So the first diagram shows air molecules, and the second one is showing a longitudinal wave using a slinky or a long spring, right? Now compressions is where the slinky is actually much closer together, and these areas are compressions where the air molecules or particles are much closer together, right? Rarefaction is where it's actually spread out. So here in this area, it's spread out here. So sound waves travel through air. When sound waves travel through air, they create areas of compression and rarefaction. So it doesn't have to be in a specific order. So compression and rarefaction. That brings us to the end of question number 3, and let's have a look at question number 4. Question number 4 is on the topic of magnetism and electromagnetism. Figure 8 shows a permanent magnet and two magnetic compasses. The poles of the magnet are labeled X and Y. So you've got compass A, which is pointing to X, right? And there's a permanent magnet, and they haven't drawn anything on compass B. The direction of the compass needle in compass A is shown. Give the names of the poles labeled X and Y in figure 8. Now, in any compass, this arrowhead is always the north, and the end of the arrow or the needle is actually the south. If that's the north, it should always be pointing to the south end of the magnet, because opposite poles attract. If that X is south, this would make it north. So X is south pole and Y is the north pole. Next question. Draw an arrow on compass B in figure 8 to show the direction of the magnetic field at this position. So if you place compass B, in which direction will it actually point? Well, because this is north, you won't have the arrowhead pointing here, right? So you should have the south end of the compass. So it should be like this, with the north pole pointing away from there and the south pole of this. You don't have to label it on there, but all they're looking for is the correct direction of the arrow. Figure 9 shows security tags in some clothes in a shop. Security tags can be detected if clothes are taken out of the shop with tags still attached. The tags are attracted to the clothes by pins made from a magnetic material. A shop assistant may use a magnet to remove the pins. Which of the following are magnetic materials? Now, there's only 4 materials or 4 types of metals which are magnetic. Copper is not one of them. Sorry, aluminium is not one of them. Copper is not. Iron is magnetic. Lead is not. Nickel is not 10. You don't have to put the cross, just the ticks. Now, iron and nickel are shown here. The other 2 is steel and cobalt. Right? It's only iron, nickel, cobalt, and steel which are magnetic. Every other metal is non-magnetic. Which of the following describes the force between a magnetic material and a magnet? Now, a magnetic material like steel and a magnet is always going to be attractive. So, it is number 1. 4.5. The shop assistant removes a security tag and drops the tag into a collecting bin. As it falls, the tag accelerates at 9.8 meters per second squared. The mass of the tag is 0.03 kilogram. Calculate the resultant force. The equation for resultant force is mass, which is 0.03 times the acceleration, which is 9.8. When you multiply those 2 numbers, you get 0.294 as the answer. So resultant force is 0.294. That brings us to the end of question number 4. Let's have a look at question number 5. Question number 5 is on the topic of forces again. The stopping distance of a car depends on the thinking distance and the braking distance. Which of the following affects the thinking distance? Now, the thinking distance is affected by anything to do with the driver, because the only person who should be thinking compared to the car or the driver is the one with the brains, right? We're not talking about electric cars like Teslas. So, the reaction time of the driver affects the thinking distance. These 2 conditions of the brakes and icy road conditions, they affect the braking distance. A car manufacturer tested 3 different types of tire which were fitted to 3 identical cars. This is the method used. So, drive the car along the road, apply the brakes until the car stops, measure the distance traveled while braking, repeat steps 1 to 3 for each car when the road is dry and when the road is wet. So, you're comparing to a dry road to a wet road. So, a car manufacturer tested 3 different types of tires. So, let's call it tires A, B, and C, which were fitted into 3 identical cars. So, they're going to drive it along the road, apply the brakes until the car stops, measure the distance traveled while braking, and repeat it on a wet and a dry road. So, the brakes were applied with the same force for each test. Give one other variable that should have been kept the same for each test. Now, they're using 3 identical cars, right? And they are using the same amount of force. What else should they actually keep the same? Remember, they're testing 3 different tires on 2 different roads. So the speed of the car should be the same, right? Because the speed affects the braking distance. So their speeds, right? You could say before braking. You could also say the section of the road that they are testing this. Section of the road tested. I'm pretty sure you can say the mass of the car as well. Next question is a bar graph. Figure 10 shows the results. So you have tire A, B, and C, and you can see the braking distance on a dry and a wet road. So these are dry roads, and that's a wet road. Dry, wet, dry, and wet. So you can see automatically on a wet road, the braking distance is slightly bigger, right? Except for tire C, the difference is much bigger, whereas tire A and B is actually just 2 meters difference. So each of these boxes, it goes, there's 5 boxes, so 5 divided by 5 is 1 meter. So this is 30, 31 meter, 43 meters, 44, that's 40, hold on, 40, this is 42, 43 meters, and this is 29, and this is 40, right? So let's have a look at the question. So let's have a look at the question. The manufacturer wants to put the safest tires on a new car. Evaluate the safety of each type of tire. Use data from figure 10. So it is worthwhile when you're looking at a graph to actually look at some of the data that's been given. So you can see tire A, the braking distance is actually the shortest except for tire C when it's on a dry road. So it's 30 in a dry, and in wet it's 31. So the difference is only 1 meters. For tire B, it has the biggest braking distance of 42 meters on a dry road and 43, right? So I would not actually use tire B looking at this because it takes far too long distance for it to stop. Now tire C is a bit interesting. On a dry road, it actually takes the shortest distance to stop, which is 29. But on a wet road, it's not as good because it takes 40 meters, right? So looking at all 3 tires, I would use tire A if it's both dry and wet. You can't just use a tire just for dry conditions unless you're driving it for a short time, like in a Formula 1 car. But if it's a normal family car, you're going to drive it in the rain as well. So you would want to use tire A, which has the shortest braking distance in both dry and in wet conditions. Right? You would definitely not use tire B. Now the difference between dry and wet conditions in both tire A and in B is only 1 meter, whereas the difference here in tire C is 11 meters here. Right? So how do we write all of these to get 6 marks for this question? Right? Well, you do it one step at a time. You literally describe the graph at one, as in bullet points, right? And then they're asking you to evaluate. So you describe, you the data in the graph, literally what you see, and then evaluate bit is basically you come up with a reasoning. Okay, why or which tire would you use? So let's have a model, look at a model answer. Right? Tire A, braking distance is 30 meter on dry road and 31 meter on a wet road. So has the shortest braking distance on a wet road. Right? Tire B, braking distance is 42 meters on dry road and 43 meters on wet road. So has the longest braking distance on both wet and dry road. Tire C, braking distance is 29 meters on a dry road and 40 meters on a wet road. So has the shortest braking distance on dry road only. Right? I'm not talking about the wet road here. The difference between braking distance on wet and dry roads for tire A and B is just 1 meter, but for C it's 11 meters. Now this is exactly what I described in the bar graph before I wrote this. So the judgment is, because we are trying to evaluate, the shorter the braking distance, the safer the tire. Tire A is 1 meter longer on dry road. Right? Tire A is 1 meter longer on dry road, but 9 meter shorter on wet road than C. Right? So when we look at this, if I'm comparing, right, tire A to C, right, it was 29 for, on a dry road, tire C is actually much better because tire A is about 1 meter more. But on a wet road, tire C is actually worse because it's 9 meters longer than tire A because it's 31 and 40. So that's what this bullet point is saying. So tire A is 1 meter longer on dry road but is 9 meters shorter on wet road than tire C. Tire A has the shortest combined average braking distance. Overall, tire A is the safest. Tire C is safe on dry roads, right, but not on wet roads. Tire B is the least safe. The manufacturer should not choose tire B. Right? Let's have a look at the next part of the question. When the brakes are applied, a force does work to stop the car. Use the physics equation sheet to answer questions 5.4 and 5.5. Write the equation that links distance, force, and work done. Now the equation is work done equals the force multiplied by the distance. Now you could use the symbols that they have given here to write the symbol equation. W, capital W equals capital F S. The braking force on a car is 6,000 newtons. So that's the force. The work done to stop the car is 300,000 joules. That's the work done. Calculate the braking force distance of the car. So W equals F S. Work done is 300,000 equals the force is 6,000 multiplied by the distance, which is S. So rearranging it, 300,000 divided by 6,000 equals S, which is 50. So it is 50 meters. Question 5.6. Explain how the force applied by the brakes affects the braking distance of the car. Now, how does the force applied affects the braking distance? Well, you apply a bigger force, the braking distance is going to be shorter. Right? So the whole idea of applying the brakes is actually to stop the car. So the greater the force, the shorter the braking distance, because deceleration will be greater. Or you could say the work done to stop the car will be the same, right? Now, these two bullet points is the best, right? The greater the force, the shorter the braking distance. Why? Because you're trying to explain, so you need to explain why. Because deceleration will be greater. It will actually reduce in speed at a much faster rate. That brings us to the end of question number 5. Let's have a look at question number 6. Now, question number 6, and in fact question number 7, is actually the same identical question as in the higher paper. So I'm going to link a separate video for the higher paper. So watch the video for the higher paper. Have a look at question number 1 and 2 is exactly the same as question number 6, which is on waves here, and question number 7, which is on forces. That's going to be on the higher video, question number 2. Thanks for watching. If you find this video useful, and if you would like to see more videos, press the thumbs up button, or the like button I should say, and subscribe if you want to follow me. Thank you.